Hello and welcome to a demo of the Wound Composite Modeler. The Wound Composite Modeler is a plugin that was developed for Abacus CAE. It's fully integrated into Abacus CAE, and it is used to generate COPV models, or composite overwrap pressure vessel models. It automates the generation of the geometry of the winding layout of the material properties. So what I'm going to do today is demonstrate first the 2D properties of the model, of the capabilities of the plugin, and then we'll move on to 3D. So the first thing we're going to do is start with a liner. Now the liner geometry is something you have presumably built in, let's say, SolidWorks or CATIA, or perhaps even with native capabilities of Abacus CAE. But once you've done that, that's the starting point of where you'll use the Wound Composite Modeler. The Wound Composite Modeler is expecting a node set or a geometry set on the liner, so you can define where the composite is going to be overwrapped. So for example, in this liner, I have this node set here which covers the entire length of the tank. So all this is going to do is tell the Wound Composite Modeler where we're going to wrap our geometry. Alright, so the first thing I'm going to do is open up the plugin. We're going to go down to Wound Composite Modeler, and you'll notice that an extra tab gets created over here. So the usual tabs are Model and Results, so now we see this Wound Composite Modeler. Now the first thing we see are some icons up top. The first one is an examples dialog, and these are just like things like the workshops or other tests that maybe you might be able to use. Let's say you're doing a 3D model and you want to do a generation of, let's say, 2 tanks. You can go through, find the examples that are pertinent to what you're doing, and have them automatically generated, and then you can look and see how things were created. The next item is something we'll see a little bit later. It's for post-processing. The third item here is a micromechanics module. Now the Wound Composite Modeler, when we're defining layers, it is expecting lamina type behaviors or engineering constant type material properties. Now if we're going to start off with just, let's say, fiber and matrix properties, well, we're going to need to convert that over to engineering constants or lamina properties. So we can do that using this micromechanics plugin. Alright, so it has a couple of different options as far as the arrangement and then the fiber volume and so on. So that'll generate your properties that you need. This item is a user's manual, which will bring up a PDF file, and this item is for entering into the sketch mode, which we'll see how that's used later. Alright, so the first thing we're going to do is just create a model, and all this is doing is it's just initializing a Wound Composite model. In Abacus CAE you can have any number of models, so you see under here I have a model. I have part 2D and 3D. So all we're doing now is just saying that we're going to generate a 2D model for a COPV tank. We're going to do a static analysis. We're going to generate axisymmetric geometry in this particular model. So all it's really doing is just initializing some things, and then we'll do the same type of thing for the tank, and it's going to have some default values for things like the element type, essentially, whether it's linear or quadratic, the specific element type, and the number of elements through the thickness of a layer. Now all of these are going to be assumed, and once we go ahead and hit create tank, we just stored the element type, and basically that's the default element type for each layer. Now as we go through and define the layers, we can override that, but so far we've just defined the default. Alright, so once we've created a tank, again, it's just initialized it, hasn't created any geometry, it's just saved some information, and now we see we've got these 5 icons. So essentially these are steps in the creation of a COPV model. So we have to generate the liner, we have to generate the composite layup, we have to partition it, and this is just for preparing it to be meshed, and then we have to mesh it, and then finally we have to generate all the material properties. Alright, so let's go to the first step. That's creating a liner. Now if we didn't have a part, we might want to use analytic, maybe we want to do a geodesic dome, and so on. What I'm going to do is just use it from an existing part. Now you see what it's looking for is a liner node set, and it's searching through the assembly. Now if we see this, we're at the assembly module and nothing is displayed. So what we have to do is instance that liner. So I'm going to create an instance, and we see now we've got an assembly. Now let's go back here, and now we see the from part, we see the liner node set. So what it's gone through and done is it's scanned through the part instances that are available at the assembly level. It scanned through the sets that just have edges on them. So this dome set is that set that I highlighted that goes throughout the full part. Alright, so the next thing we're going to do is enter the transition radii, and I'll explain what that means in just a second. What I'm going to do first is check that everything looks like it's being read properly. So I hit the sketch mode, and now what we see is a bunch of points that generate the liner, and you'll notice this is a dash line. So that node set, this dome set, that essentially terminates at this point, and then the plugin just assumes that if any layers go beyond this point, which they actually shouldn't, but if they do, then this is just going to be extended vertically to infinity essentially. And we see the same thing down here. So with this sketch mode, it lets us right away determine if our node set was created properly or if it's being read properly. Then the next thing are these two transition radii, and what these represent is as we're building the geometry of these layers, now we have some nice analytic expressions that define how the layers build up, around the cylinder and then around the dome, but these things don't work very well right here near the polar boss. There are just too many different things that can happen that can change the geometry in the polar boss. So we really need some tools to let you change the thickness buildup right at the polar boss. Now the first step in that is defining this transition radius, which means that as a layer is building up and it's following those thickness buildup equations, follows them up to the point where it hits this transition radius. And then once it does that, then the slope of that layer, the outside of the layer, just remains constant until it finds an intersection with the polar boss. Now, we've got some other tools to give us a lot more flexibility on how that buildup occurs. But right now we're just saying we have a default transition radius for every layer of 2.5 for the top and the bottom of the liner. Now we can, as we create these layers, we can override that, but this is just the default. Alright, so when it goes through, when we save that, it's going to go through and it's going to check all the sets and do a bunch of error checking to make sure it looks right. And then once it's satisfied with that, you'll see this green check mark. It means this first step is completed. Alright, the next item is generating the composite layout. So I'm going to double click on that, and let me just move this into view here. Alright, so we see a bunch of icons up here. These are for adding rows, deleting rows, moving a row up and down. This is again for entering a sketch mode. The refinement, all that is the number of points that are used to define the liner, and then all of those points propagate up through as each layer is created. Coarser refinement means the sketching draws more quickly, but in some areas as one layer overlaps, the geometry is not quite right. A medium refinement is usually enough to get really nice geometry and still draw it reasonably fast. Alright, now there's some icons for displaying the options. Now what we're seeing here is a layer, and it has a bunch of controls displayed. Now these are the default controls, as if I'd hit these default columns. Now there are lots of options for every layer, so if I were to click this visible columns, let me move this into the field of view. Now these are all the different options that can be used for every layer. Now most of these have defaults that we don't have to worry about. But just so you know that if we want to display any particular layer, we can hit this and then choose the one. Now typically we use the default, but now if we wanted, let's say we're changing some geometry and we're tweaking how the tank builds up at the top of the tank, then we can display this top columns, and you'll see it has all the options for the top termination, top radius, a bunch of other controls just for the top. Likewise, we could do the bottom. This item just shows everything, which we don't really want to do unless we've got a very big monitor. This one shows mesh controls. For example, if we want to override the mesh controls, we can set the number of elements through the thickness of a particular layer, or change the element formulation. So this might be useful. Let's say that you have the first layer is a uniform thickness, let's say a rubber shear ply. So you might want to change the element formulation to a hybrid formulation, and maybe change the number of elements through the thickness. Alright, so let's go back to the default here. Now what I'm going to do in this case is this particular tank, even though the top and the bottom of the dome are slightly different in geometry, they're roughly the same radius. So I'm going to hit this icon, and what that's going to do is it's going to tie all the bottom controls to the top controls. So that way I can display just the top columns and work on that. So first of all, we'll enter some basic things. For example, the material name, we'll put the first wind angle is 5 degrees. Now this tank has a radius of 12, so I'm going to put a thickness of 0.1, then a bandwidth of 0.1. Alright, so I'm going to start off and just sketch the tank, and let's kind of zoom in over here. And we see a couple of things here. We see the dashed line that represents the liner that we've already defined, and we see this layer coming up, and it hits this dashed line, which is the transition radius, and you'll notice that once it hits that, whatever the slope is, it just remains constant until it finds an intersection with the polar boss. So this would be our first helical layer, but what I want to do is I want to make a few changes here just to demonstrate how we would control the thickness buildup in this area. So what I'm going to do is switch over from a helical with no friction. Now helical with no friction, all you give is the wind angle, and it looks at the cylinder radius, and from that it determines where the layer would turn around, or where it would terminate as far as the radius is concerned. Now if we do a helical with friction, we can actually control the radius. So now this point here is a radius of 2. So what I'm going to do is I'm going to put the radius out here and then move this transition radius, so it just kind of draws the layer terminating by itself without interacting with the polar boss. So I'm going to say a radius of 2.3. Alright, I'm going to display the top. Now this transition radius, I'm going to move inside so it doesn't conflict with the way the layer is terminating. So I'm going to say a transition radius of, let's say, 2.2, so it's slightly inside. Now I'm going to go over here and hit the refresh, and we see the layer now starts to look a little bit different. Now at this distance here, this is the end cap, and the distance from this point, if you would draw a line down here, this distance by default is 1 times the bandwidth. So let's say we want to change the shape of these end types. What we can do is this end fraction controls that shape, so I could, let's say, change it to 1.5, and we see it backs up quite a bit. Or I can go the other way, hit refresh, and we see it now, it makes it a little bit more buildup. All right. Now let's say that this particular layer, let's say that we're satisfied with the buildup up until this area, but this thing, let's say it tapers down. You know, in reality, when we look at the tank that's been built, we say in reality, let's say it terminates roughly at this point here. Now, how would we do that? Well, what we're going to do is take that transition radius and move it over here, because if you recall, wherever the transition radius intersects the layer, then that slope remains the same. So I'm going to set the transition radius. Here it is. Let's say set it to 2.6 and refresh. So now we see this thing has moved up over here. Let's move it back a little bit. Let's say 2.9. Okay, so we're very close now. Let's say we have to go up a little bit. Now there's one other thing we could do, is this is the transition angle. So this slope doesn't change once it hits this vertice. If we wanted it to thicken up, we could change this transition angle to a positive number. So let's say 2.0 degrees. Okay. Or if we wanted to thin it down, let's say negative 2.0. Not two negatives, one negative. Try that again. So we see it's thinned down a little bit. So in reality, we probably want about 1.0 if we want to hit that point very closely. Okay, something like that. So the point is, we can change this slope. We can move this down, and once we hit this radius, then we can control how that line terminates. All right. So there's our first layer. All right. Well, next thing I'm going to do is add a hoop. Now the way we add layers is we put our cursor somewhere in the table and we hit the plus sign. Now what it does is it copies every single control over from that layer to the next one. So now I've got to change some things. I've got a hoop. I've got 90 degrees. Oops. Now I'm just showing the top controls. What I'm going to do is I'll just show the default controls here. Thickness, we'll keep at 0.1. Top termination type, we're going to terminate it by the Y coordinate. And what that does is it now expects us to define where the hoop terminates by determining a distance from the center of the tank. So the center of the tank is here, and that's based on that node set of the liner. It calculates the average between the 2 points, the max and the min. So then we're going to add some distance here where the hoop is going to terminate. In this case, the tank has a length of 8, so I'm going to put a Y coordinate of 5. Alright, so let's go ahead and redraw it, just for sanity check here. Now in this case, the end type definitely does not look right as a default, so what I'm going to do, because it's using the same controls that the helical does, so 0.75 means this distance is going to be backed by 0.7 times the thickness of this particular layer. So that doesn't really quite look right. So what we're going to do is go hit the top controls, and the transition override will say it's 1.5 is more reasonable for a hoop. Okay. So now we've got our hoop and our first helical. So what I'm going to do is add another helical. So I put my cursor on the row of the helical. Now, let's say instead of 5, it's 10.0. Again, since it's helical with friction, we're controlling where it turns around, which is a radius of 2.3. So let's go ahead and just redraw it as a default. We'll just see what the default values are going to look like. So we see it builds up and terminates here. Let's say that this, in reality, this thing actually, the peak of this actually backed up a little bit. Now what we could do is change that end fraction to, let's say, 1.0. Okay, because remember that termination is around here, 2.3, so the point where this would start to break off from the analytic expression, which is here, it would start to taper down based on this distance of the bandwidth times this fraction, which is now 1.0. So we back that off a little bit. Now let's say it terminates, let's say at the middle of this point. All right, so we probably want to move this thing back a little bit. So transition radius, let's say 3.1. We'll update it. Yep. Maybe 3.0. And maybe 2.95. Okay, now I'm just going to use the transition angle here, and I'll change this over to, let's say, 5.0. So there we go. That's pretty close to the center there. So I can get pretty close to what I might see on an actual tank. Now what we'll do is we'll just add one more hoop here. And usually these are stepped back. They're usually not piled all exactly the same height. So what I will do is the y coordinate, I'll say, is 4.5. So we'll refresh it one last time. Now we could just keep generating layers, but just for the demonstration purposes, I'm going to go ahead and say this is okay. Now, so far all we've been doing is working in the sketch. We haven't created any parts in Abaqus, nothing like that. So once I hit OK, now it's actually going to go off and generate a part. So now we've got our first 2D part. We've just got the geometry layout. Now if we were to mesh this, the mesher would tend, with these really thin layers, it tends to skew the elements a little bit. So to correct that, what we do is we put partitions, or in other words, we draw lines like perpendicular to these layers. And that kind of forces the mesher to keep those elements nice and square. So the next step is to generate the partitions. So I'm going to first we'll just try using the defaults. So I'm going to enter the sketch mode. Now what we see is in dashed lines we see the composite shown, and then the solid lines are the partitions. So based on these numbers, which is the number of partitions and then the biasing, whether we want to put more in the polar boss region or more to the cylinder, shows what the partitions will look like. Now what we're looking for is we don't want lines to be too close to an existing vertex. Now these vertices are going to be drawn, and they're calculated from all the underlying geometry and the layers and certain properties of the layers. We just want to make sure none of our partitions are too close, otherwise the mesher will have to try to put a mesh in here. That's probably a little bit too tight. So in some cases it might actually fail. It might not be able to generate geometry. Other times it may, like in this case, it probably would be able to, but it would generate some very skewed elements. So what I'm going to do is remove this particular partition. I'm going to hit this button here, and then it says select lines to remove. So I'll remove that one, and then I'll kind of zoom in here and see if there's any others that are too close. I think these are fine. That one's probably fine. See, that one's a little close. We probably should delete that, but I'll just let it go. And then we look in here, and I think these are okay. We're going to have some elements that are a little bit tight there, but I'll go ahead and hit done. Now, it says it's removed one partition. It kind of keeps a count. Now, if you want to redo it, you can just hit this refresh, and then it'll add that partition back in, and then you can go back and remove some others. I'll go ahead and hit create. Now it's gone off and generated a bunch of partitions for us. Now one thing you also notice is it generates these partitions at the end of the layer. That's because what it does is it forces this mesh to be hex or quad elements in 2D, and this is quad dominated. So it'll, depending on how sharp this is, it might be useful to mesh this with, let's say, a triangle right at the tip. So it improves your meshing, so that's why that partition's there. Alright, so we got our partitions. Now we're ready to generate a mesh. Number of elements along the tank, I think I'll reduce that from the default. So we've already specified the number of elements through the thickness of the layers. All this was doing is specifying the number of elements along the length. Okay, so now we see that we get some nice square elements in here. And we can even see as we run over the layers. Now, now you can see where the partitions are here. So you can see why they're so square is because of those partitions. Alright, so the next step is we've now generated our part, we've got all the geometry, we've got it meshed. Now we've got to generate material properties. Now what we've done so far is we entered one material for each layer. Now what happens is, as this wind angle, let's say, goes over the cylinder, let's say at 5 degrees, and then it moves over the tank and then it wraps around the polar boss, that wind angle is continually changing. So the way we're going to, and the reason we can generate a 2D model, an axisymmetric model, is because when these bands are put down, they're basically woven. So one band is put down, it comes around the back of the tank and comes back at the same angle, but now it's at an opposite angle, so it's like 5 degrees and -5. And you see these are woven together. So they're basically at the same same coordinate through the thickness, but they are woven. So what the fortunate thing about that is that we can assume that the behavior of that is axisymmetric. Now, to run an axisymmetric analysis in Abaqus, well, you have to have the material coordinates in the global direction. So x, y, they've got two of the axes have to be in the x, y, and the third has to be in exactly in the z direction. So in order to generate the material properties for wind angles that are clearly not in those directions, what we have to do is transform the material properties into some global directions. So the plugin has got to do that for us. It's just too tedious to do. So we'll hit the properties, and now what we'll see is a wind angle increment. Now what that does is, instead of creating a material for every single element, which would, in the first place, it would take a long time to do in Abaqus CAE, but it'd also slow the solvers down. So we want to kind of group them together by some increment of wind angle. So we'll kind of discretize the wind angle changes. Alright, so as a default, we'll just use the 0.5 degrees. Now if we have a UVarm subroutine, or if we have a Fortran compiler, we can include the UVarm subroutine. And what that'll do is, when we're post-processing it, we can get the stresses in the fiber direction. Otherwise, the stresses will be in our global coordinate system. So I'll go ahead and generate the user subroutine. We'll hit generate properties. Okay, so now we see our final check mark is done, so we've got this tank all ready to go. So let's just look at the material properties. And you'll see what we see for these two hoops is the color is the same, so all of those have the same material because they're all at 90 degrees. Now for the helicals, you see that they get broken up a little bit. So down here in the cylinder, they all have the same wind angle, but the wind angle starts to change. So like this color to this color is a change of about ½ a degree. So around the cylinder, the wind angle changes fairly slowly, but as it gets up to the polar boss, it changes very dramatically. Now in this area, you see all one color, and the reason we see one color is that all of these fibers are all at 90 degrees. Now this distance by default is 1 times the bandwidth. So let's say, for example, in this particular layer, well, maybe because of the number of circuits, maybe that's not so accurate. So maybe we believe that a better approximation is to have about half of this at 90 and then have all these transition up to that. So how would we do that? Let's go back to our layer manager. And what I'm going to do is I'm going to display, oops, let me move this into the field of view here. I'm going to display a couple things, our 90-degree factor, and then I'm also going to change, make the wind angle on the bottom different from the one on the top. Okay, so what I'm going to do is at the exterior layer, I'm going to say a 90-degree angle of 0.5. So that means half the bandwidth. The bandwidth is 1. So at a distance of 0.5, we'll have everything at 90. Alright. Now what I'm going to do is, here I'm going to include a bottom wind angle also. So the top wind angle is 10 degrees. And maybe I'll change the bottom to 15. Alright. So I'll hit OK. Now the part gets regenerated. Now we've got to just go back here. Since the geometry changed very little, we'll just keep everything we've already generated. Okay, so I'm going to set it to defaults, regenerate the properties. Alright, so now let's look at the materials again. And now what we see is this top layer now has a much smaller distance at which they're all 90. And then you'll also see the color start to change on the outside because it's transitioning from 10 degrees to 5 degrees in this outer layer. So we can control the wind angle along the cylinder and allow it to vary linearly. So now the job is pretty much built. Now we just got to go and do a few things in Abaqus to get this thing ready to run. So for example, we could create a pressure load in step 1. I've got a surface defined of the liner, inner surface. Let's say 1,000. And we can create a boundary condition. Let's just fix the job in the Y direction. I've got a node set there. Y symmetry. Now one last thing we'll do is we'll assume that this is a bonded liner, so we're going to put a tie constraint between an outer surface of the liner and the inner surface of the composite. Alright. I'm going to create a job. Actually, I think I've got one generated already here. Okay. So I'll submit it. Now we can do a little post-processing here. Now the first thing I'll usually do is I'll look at UVARM 1. That's the wind angle, just as a sanity check. So we see that same type of pattern. Alright. UVARM 1 is the wind angle. Now if you're wondering what all the UVARMs are, these are generated from the UVARM utility. We can just click this button and it tells you UVARM 1 is the wind angle, UVARM 2 is the strain in the fiber direction, and the stress in the fiber direction is UVARM 5. Okay. So I can go UVARM 2 and see the strain in the fiber directs, and UVARM 5 will be the stresses. Alright, so if we want to also do some path plots, that's what this item is for. So let's say I'm going to do UVARM 5, which is the fiber stress. I can just highlight these, hit apply, and it plots the stresses out along the length of the tank. So let's say I want to get rid of some of this noise. We can put a little smoothing on here. Okay. So we can get an idea what the stresses look like. So you see the spikes and the stresses and the strains as one layer overlaps another. Alright, so now let's just briefly demo the 3D capabilities. So the hard part's already done. We've generated the layup. So what I'm going to do is create a model of 3D. So very similarly, we'll go through and do this again here. So we'll say 3 segments. It's going to ask for the axis of rotation, which is there. And I'm trying to limit the size of this thing, so I'm kind of running out of space here. So we'll hit create just to initialize our tank. Alright, so similarly we have the same type of thing. We have from part, we have the 3D dome set. I'll set the transition radius at 2.5. Just trust that that's graded properly at the manager. Now what I'm going to do here is import from our other model, move this into, which is from part 2D, so it imports everything for us. Okay. So we see the same type of thing except in 3D. Now we can do the partitions, and what we'll see is exactly the same thing. We'll see this one that we wanted to remove, and we'll just stick with that one. Now this takes a little bit longer because since we're working in 3D, the partitioning tends to slow down. So let's say we had a tank that had a very long cylinder. Now, since the partitioning slows you down, what you might want to go do is remove a bunch of the partitions, let's say in the cylinder region, and just keep most of them in the dome regions. All right, so we're going to stick with 600 elements along the length. So we have 3 segments, or instead of using a default of 6, we'll say in the middle segment we want more elements for whatever reason. Once the mesh is created, we'll go off and generate the material properties. Okay, so once the material properties are, and then display by material. Okay, so let's zoom in here. So now we see our 3D geometry, bumps right up into the polar boss nicely, and we see all our different colors. So you'll notice you see bands of the same color, meaning the wind angle is the same as it goes around the hoop. Alright, so that pretty much wraps up the demo. We've gone through and we've demonstrated how we use the sketcher to very easily generate the geometry of a 2D tank. And then if we need to, we can generate a 3D model and just import all of the difficult work, which is the layup generation. We can import that directly into the 3D model, and we can post-process it, and we just demonstrated how the UVARM subroutine is used. So if you have any questions, please contact the Simulia South office, and we'll be more than happy to answer any questions you might have about the plugin. Thank you very much.